Now I want to show you why this theorem is true. And to understand what I do here, all you really need to know about matrix multiplication is that it works and that these two formulas are correct. So you're just going to have to take my word on that. But that's all you really need to do, is just accept that I know what I'm doing and I wrote these down correctly here, and that matrix multiplication actually works. If you believe those things, then you're going to get something from this video. All right, so moving forward, in this example, I'm going to use k equals 2 in the theorem, which is the number of walks of length 2 we're talking about. And remember, this is the a squared ij entry, gives the number of walks of length 2 from vi to vj. So we'll look at these two entries here. A squared 2, 1. Let's look at a squared 2, 1 first. Remember, as we found before, this is the number of 2 edge walks from v2 to v1. And we already know the answer of that one. Right, let's just do it again. The number of walks of 2 edge walks, number of walks of length 2 or 2 edge walks from v2 to v1. And there's only one of them. You can go up here and go there. So v2 to v3 and v3 to v1. Right, so there's only one of them, so the answer is 1. And now we're going to see why we get that answer. All right, so something to notice here, first of all, is that this is the truth, right? As we've defined walks, this is the truth. Now we want to see, how does matrix multiplication and the dot product specifically, how does it do this thing? How does it make this computation? All right, so this is the dot product, and this is the dot product of the second row and the first column. All right, so A21, all right, okay. So that's something I should also mention, right, is that this is the adjacency matrix A. This is the adjacency matrix, right? So it tells if there's an edge or not in my graph here. So this first computation, we have A21. That's this one right here. And that corresponds in the graph to this here. Right, so there is an edge, that's a 1. Now, A11, that corresponds to that 1, or that 0 right there, right? And because there's a 0 there, that 0 corresponds to the fact that there is no self-loop there. So if you think about it, right, this is a 1 times a 0, which, as we all know, is 0. But what is that really saying? It's saying one edge put together with no edge. One edge put together with no edge gives no 2 edge walks. Now moving on to this next one. A22, that's 0 there. That corresponds to no edge from v2 to itself. And then A21, that's that there. So that's that there. So again, we have 0 times 1, where we have no edge put together with one edge does not create a 2 edge walk. That's why we have a 0 there. The 0 you can think of as no edge, and 0 times 1, nothing, right? There's no two-edge walk. Now I'm running out of colors here, so I'll have to recircle or recycle these colors. A23, that's that right there, that corresponds to that edge right there. That's a 1. A31, let's see, down 3 over 1, that's that one. That corresponds to that there. And in fact, you see that is the 1 that we got right here, right? That is the 1 walk that we got, right? So in blue, this number A23 here, this is saying 1, and this A23 being a 1, that's saying there is an edge. So we have an edge from V2 to V3, and this number A31, that's saying there's an edge there. So an edge put together with an edge gives you a two-edge walk. That's the 1 there. And to contrast that now, A24 is a 0, right? That A24, that's that non-existent edge there across from 2 to 4. That doesn't exist there. So no edge put together with A41, no edge put together with one edge still doesn't give a two-edge walk. That's why we only have 1 total. Now let's look at the A squared 2, 4 entry. A squared 2, 4, that's that one. That's the number of two-edge walks from V2 to V4. Now, how many of those are there? From V2 to V4, maybe we found 2 of them, right? Let's see. We found that one, V2 to V4, and that one. So the answer, the answer is 2. We can see the answer is 2. Now let's see how this is computed. All right, so now we're looking at this one. So first of all, we've got A21. So down 2 over 1, A21, that's that right there. A14, let's see, so first row, 4th column, A14, that's a 1. You see now that's a 1 times 1. There is, so this first one right here, that's saying there is an edge from V2 to V1. If you put that together with there is an edge from V1 to V4, then you have 1 two-edge walk. Now A22, that's a 0. That corresponds to there is not an edge from V2 to itself. Let's see, A24. A24, you can see that's going to have to be a 0, and A24, in fact, is a 0, right? That's saying no two-edge walk from V2 to itself, and no two-edge, no edge from V2 to itself, and no edge from V2 to itself. That's this. That says that right there. That's saying that being a 0. That's saying no edge from V2 to itself put together with no edge from V2 to V4 is no two-edge walks. Doesn't account for a two-edge walk. All right. Now let's go to A23. A23 again. Let's see. A23 down 2 over 3. That was a 1. Okay, there you go. There's a 1 there. And A34, down 3 over 4, there is a 1 there. That's that one. You see how that goes? They go together now? Right, so 1 times a 1. So yes, the 1 is saying, yes, there is an edge from V2 to V3. And then the second one is saying, yes, there is an edge from V3 to V4. So a 1 times a 1 is a 1. That accounts for the other one. So there's one of them, there's 2 of them, that's 2 of them. So you can see this entry right here, this is going to have to be a 0. So why is that a 0? Let's see, 2, 4, and 4, 4. Yeah, both of those are zeros, huh? Let's see, 2, 4, there's nothing there. And 4, 4, nothing there. All right, so that's how this theorem is working. That's how it's really just a matter of this beautiful way of interpreting multiplication for matrices.